All right, so in this video, we're going to do a moving average process. So the difference with the moving average process and a weighted moving average for smoothing fluctuations, we'll write that out first. So if you're going to smooth out period to period fluctuations, then you may use let's do n. So m for moving average over n many periods. You weight all the periods the same. This would give you maybe xt. Maybe this would be m n comma t for at that time. It's just a moving average. So this is not a moving average process, but this would be a moving average to smooth out data. Or it'd be minus n. It would be minus n minus 1. So this is for smoothing. And that would be maybe if you're trying to fit a polynomial or something to the data. But for us, for this in time series, we're going to talk about a moving average process. So for the moving average process, this weights so for this smoothing moving average, it weights all equal. So they're all equally weighted. They're all weighted by 1 over n. They're all weighted by 1 over n. But for a moving average process, it's a weighted average. It's a weighted moving average of previous error terms. So it's a weighted moving average for a previous error term. So for a first order moving average, so let's do a moving average of the first order. What's going on here? It's like my say there's a problem with my pad. So for a first order moving average process, let's say xt is equal to an error term plus. So if it's the first order, that would mean it's a weighted average of previous error terms. So theta will be our coefficient of our previous error term. So it's a first order or an order of 1. So we're only doing one lag. So one lag of error terms. And this is in our moving average process, epsilon t, our error term, for t equal to 0 and 1 and 2 and so on. It is IID with 0 mean and a constant variance. So it's a 0 mean white noise process. So our epsilon t is a 0 mean white noise process. And our xt is a moving average process. Moving average process of order 1. So ma of 1. So remember, moving average process is weakly dependent. So how do we know that it's weakly dependent? How do we know that it's stationary? So we can prove it. We know that, well, right off the bat, we already know what the expected value for the error terms are, and that's 0. So now let's, so for the first moment, we already know that it's going to meet that criteria. But what about the second moment? What about the variance? So let's calculate the variance of xt. So the variance of xt, remember back in chapter 4, whenever you do the variance of this, we'll go ahead and do it all. So since the error terms are uncorrelated with others, because there are no autocovariances, the error term is a 0 mean white noise process, we don't have to worry about any covariances. So the variance of xt, the variance of x is going to be equal to the variance of our error term plus the variance of our theta error term. Theta times our previous error term. So right off the bat, we can simplify this a little bit more. So this would be equal to the variance of our error term plus, and you can factor out the theta. So if you factor out the theta of the variance, you get theta squared multiplied by the variance of our error. Then you can simplify it a little bit more. You can factor out the sigma squared, and you get 1 plus theta squared multiplied by our variance of error, a variance of the error term. So this is our variance of our first order moving average process. So now let's calculate the covariance. The covariance of xt, and let's do xt minus 1. You can simplify. You can simplify from all of this because the error term is IID, independent and identically distributed, and with a mean of 0 and a constant variance, and there are no autocovariances. We just get the theta, our coefficient, multiplied by the variance of our error term, which would be equal to theta times sigma squared. So this is our covariance. This would mean that the correlation, remember that correlation. So the formula for correlation, I'll use rho for correlation. This would be equal to the covariance. The covariance divided by the product of the two standard deviations. So that would, in this case, that would just be the variance, because it's the same. It's the same value. So now our correlation in this case would just be the covariance between these values divided by the variance. So theta times sigma squared times variance divided by 1 plus theta squared multiplied by our variance. You see that the variance cancels out. The variance cancels out, and we're left with this. So it simplifies to this. So this is the formula. This is the formula for the correlation, or the auto correlation. This is the formula for the correlation between xt and xt minus 1 for a moving average, or a first order moving average process. So for a first order moving average process, the absolute value, so in order for this to be stationary, the absolute value of theta is going to be equal to or less than 1. And this would mean that our correlation, the absolute value of our correlation would be equal to or less than 0.5. Because with this formula, it can't be greater than 0.5. As long as theta is less, or the absolute value is 1 or less, then the most this correlation can be is 0.5. And this is so this was for a first order moving average process. To make it general, a general moving average process, so a Q order. So the order is notated with Q. So an MA, a moving average process, order of Q. This would be written out as XT is equal to the current error term plus theta 1 times the previous error term plus all the way to theta Q multiplied by the error term of T. So it's Q mini lag. So T minus Q. And again, this is where our error term, epsilon T, for T equals 0 to, and so on, is IID, independent and identically distributed, with a mean of 0 and a constant variance. So this is where the error term is a 0 mean white noise process. So it's purely random. So this is it for a moving average. The next video we will do autocorrelation.